We've advanced quite a fair way now in our complex analysis course. In fact, we're coming close to the end of this part, and then we're going to start the last chapter, which will be the Fourier integral. That chapter will focus on the applications of this stuff to calculating some infinite integrals there. That's why we do this chapter as a prelude to Fourier integrals. But to help you get back on track, let me just recap where we are in the game now so that you can see clearly the bigger picture. I wish more people were attending classes, then they could see how we have progressed and what we have achieved so far. So let me just list a few of our achievements so far. 1. So if you have a closed contour, I'll just summarize things so it doesn't look too detailed. If you have no singularities in a certain closed contour within it, then the line integral along the contour of f of z dz is precisely 0 if f is analytic or holomorphic in that region. This is called the Cauchy-Gorsac theorem. Now, if you have a singularity in a closed region like that, then we've got a trick to handle that also. We have Cauchy's integral formula. So it's not just a straightforward f of z, but it could be like f of z over something. So it could be f of z over z minus z naught dz. And according to Cauchy's integral formula, this is simply 2 pi I times f of z naught. What a neat formula. The line integral on a contour C of f of z over z minus z naught. So z naught is a point of singularity. This didn't happen here. If there's no singularity, the line integral is 0. If there's a singularity, then there's a formula. 2 pi I times f of z naught. Plug in the z naught into the top numerator, and the game is over. The answer is the integral. Thirdly, okay, let me swap the order here. Let's take the extended form of this. What if you have more than one of these singularities at the bottom? In other words, suppose you have f of z over z minus z naught into z minus z1 dz. Then what's the story here? You sum the two parts, and you will get, this can be the contour integral across C1. You write it like this, f of z over, well, f of z over z minus z naught, for example, and z minus z1 dz, plus contour integral of f of z over z minus z1 all upon z minus z naught. You disguise it like that. So each one will be 2, this will be 2 pi I f of z1 plus 2 pi I f of z naught. And you can have many of these poles, singularity. I just dealt with 2. So that's the next level of difficulty when you have more of these. Linear poles, as it were. Then the next question was, what happens when you have like a pole that's repeated, z minus z naught to the power 3? Then you have to use differentiation. So now if you have repeated poles, repeated singularities, example, if you have the integral of f of z over z minus, okay, let's write the formula down, z minus z naught to the power k plus 1 dz. This was 2 pi I over k factorial, and then you take the kth derivative, so it's f of k at the point z naught, the kth derivative at z naught. So that was the first part of the work when we achieved all of these results. Then we made a startling observation. When you look at f of k over k factorial, that bears a stunning resemblance to the Taylor coefficient. When you expand a sequence, expand a function as a power series, the coefficients are kth derivative of k factorial. So there's a connection between this and the Taylor series. But actually, the problem lies in the fact that Taylor series has only got positive terms. So we have to extend our understanding of series. Then we have to have terms with negative exponents, like 1 over z squared. That would give you negative exponents, z to the minus 1, z to the minus 2, and so on. So now the story took a different turn, and then we found that a special term, the k is, when exponent is minus 1, that caused, so when k is minus 1 here, see here, k is minus 1, z minus z naught power 0. So this guy disappears, 1. That special term, B1, is called the residue. So you can work it out with this same formula. That special term is a residue. So if you work out the coefficient of 1 over z, or 1 over z minus something, as long as the power is 1 over z to the power 1, that coefficient gives you what we call the residue, and that residue is the integral of something. If you ask to integrate something with that property, then you simply find the residue. Expand it as a series and find the residue. And then I also explained how you find residues. Let me just jot down a few of these thoughts here so that you can have them in one place. So I broadened this understanding to Laurent series. Where I said that a function f of z can be expanded as some ak z minus z naught to the power k equals to naught to infinity. That's the Taylor series part. You have positive exponents. Plus, you could have some bk z minus z naught to the power, what is over k, right? So it's minus k, from k equals to 1 up to infinity. If it stops at some number n, let's say it goes from k equals to 1 up to 3. In other words, you stop at z minus z naught to the minus 3. Then we say the pole is of order 3. The highest order of the negative exponent is the pole of the, is regarded as the pole. It has a pole of order 3. Okay, most of them do stop, but it can also go up to infinity, in which case we call it an essential singularity. You can't do anything about it. You can't remove it. So the AK here, we know from the earlier study, 1 over 2 pi I integral of f of z over z minus z naught dz. Or let's take this over some contour C then, or C1 if you like. This here, bk, is likewise the same thing, but I write it like this. 1 over 2 pi I, let's say some other C2, f of z over z minus z naught power k minus 1 dz. So the significant coefficient is b1, that is 1 over 2 pi I, the line integral over c2 of simply f of z dz. And then we said B1 is called the residue. B1 called the residue. And it is the highest, or it's the coefficient of 1 over z, or 1 over z minus z naught. The power 1, that is, of course. I need to write that. So that's the Laurent series. And that, by taking B1, we find that we can actually establish that kind of an integral. If you take the 2 pi I across, the integral of f of z dz is 2 pi I times the residue of f of z. All you need to do is find the residue. Now, finding the residue is a story. I'll come to that now, but let me just write the residue theorem to clinch this last part here. So the residue theorem is stated like this. That the integral of some function f of z dz, where a certain function is holomorphic, except at certain finite number of points, z0, z1, z2, whatever it is. In other words, we're saying that if you're trying to find a certain contour integral, a line integral, of something that's positively oriented. By the way, there's two types of orientation, positive and negative, and we're supposed to speak about that. But we will treat all of these as positive in future. But negative orientation makes a difference. There's a minus sign enters the picture, as we've discovered in some examples. So if there are some bad points inside here, we can draw circles around them, isolate them. Technically, we can draw some tubules connecting them to the outer one, where the direction will change inside, so it will go that way. It will go opposite to the C. Let's call them C1, C2, C3, and C4. This is going that way, this guy will go this way. And up there, this guy will go that way. So the C's are clockwise, while the capital C is anti-clockwise. If you want to work out the line integral along C, the answer is exactly the same as working out the residues of each of these points. In other words, line integrals along the C, around the singularities. It actually doesn't matter what the shape is, as long as it's a closed region. Around the singularities, you can just throw around them circles. Surround them by circles, work out the residues, and the game is over. So this can be written as 2 pi I. You want the residue of f of z, and you can take at every z k and sum them. K equals to 1 to some number n. If it's 3 singularities, it will be 1, 2, 3. So z1, z2, z3 singularities. Right, so that's this very straightforward formula. And we already know how to find the residue so far. You expand it in a series, you read off the coefficient of 1 over z. That's the classic approach. That's the first principles approach. But subsequently, we learn that there are some simpler ways of doing it. Like, who wants to work out a series all the time? Take some time to work out all the coefficients and stuff. But if it's trivial, that's a way to do it. If you know it, like it's a sine z or something, you may know the series z minus z cubed over 3 factorial, blah, blah, blah. Then you can read off stuff. But if it's more complicated, then it requires some other tools. So let me now deal with some methods of finding residues, which I've done, right? This is just a review. I hope you understand. I'm not doing anything new so far in the first, say, 20 minutes. I will do something new shortly. But I just want you to see the big picture. Methods of finding residues. Otherwise, you'll be able to do a whole bunch of calculations, but you don't know what they mean. Where's this taking us? then it's pointless. You should understand something. Oh, I should have started a new page. Okay, let me start it on a new page, finding residues. Finding residues. So there are a couple of cases that work nicely. About 4 have got nice, clear ways to read. Number 1, F analytic everywhere. In other words, there's no singularities. Then the residue is 0. F analytic everywhere, residue is 0. If you have F of Z is some G of Z over Z minus A. And of course, G of A must not be 0. You can have a 0 on the top. Then the residue of F of Z at Z equals to A is simply G of A. You plug this A into the top, and that's the answer for the residue. I proved this. I expanded this as a Taylor series, and I did some revision and blah, 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 and I achieved the result. So I'm not going to prove all those things again. Thirdly, what's our type? P over Q. F of Z, if it's the polynomial, P of Z over Q of Z. But importantly, you can have Q of A equal to naught, but you cannot have Q dash A equal to naught. Then in this case, the residue of F of Z at Z equals to some singular point A, simply P of A over Q dash of A. If you got like a polynomial over a polynomial, you simply differentiate the denominator and plug in the point where you find the residue. Easy as that. Again, I proved why that is the case. I expanded a series, I showed you the coefficient of 1 over Z is that. Go back to the proofs there. And one last one on the scheme. 4. What is the last one? When you have a repeated pole. You have a repeated pole. So F of Z is some G of Z over, let's say, Z minus A to the power N. Z minus 2 cubed or something. What then? So now we have to use differentiation. The residue of F of Z at Z equals to A is simply 1 over N minus 1 factorial. Then you take the N minus 1 derivative, dN minus 1, dZ N minus 1 of G of Z. So if there's 3 Z minus A cubed, then you have 1 over 2 factorial, A minus 1, 2 factorial. And then you have second derivatives. So you take G of Z, whatever the numerator is, differentiate it twice. You can plug in A. Z equals A. Plug in Z equals A, that's the answer. So all bases are covered now. We've covered repeated poles and multiple linear factors and so on. So all kinds of, well, polynomial types, guys. We haven't come across log Z and e to the Z and e to the I Z and stuff. Those are some weird ones, which also have a meaning. But these are the basic ones that you're supposed to look at and then work out the residues just by examination. Just by looking at it, examining it. So let's take an example or two. So here's a simple example, just to practice this residue theorem. So let's take an example like you've got f of z equals 2, 2z to the power 6 plus 5 over z minus 3 to the power 4. Find the residue at z equals 3. Now this one is looking like that. Z minus 3 to the power 4. It's looking like case 4. So that's the trick we're going to use here. So the solution will be the residue of f of z at z equals 3 will be 1 over 3 factorial. Why 3 factorial? Because n is 4, right? Z minus 3 to the power 4. Don't get confused with this other thing here. Another 3. It's a different guy altogether. There's 1 over 3 factorial. Then I must equal this to the third derivative, d3 dz cubed. I must differentiate 3 times. So it will be d3 dz cubed of 2z to the power 6 plus 5. And then I'm just plugging in 3 at the end of the game. So let's do this. You can do it step by step. That'll be 1/6 d squared dz squared. Let's do one derivative at a time. 6 2s are 12 z to the power 5 plus 0. The next derivative will be 1/6 of d dz. 5 12s are 60 z to the power 4. Last one, 1/6. So d dz will be 240 z cubed. Now we plug in z equals to 3, so it becomes 1/6 of 240 times 3 cubed. It's 40 times 27. 1080. That's the value of the residue. And that residue will be used to compute some integral. The integral of something is 2 pi I times the residue. So this might have a times 2 pi I in the future. Okay, so you can see the three derivatives. That's really what you have to do. If you expand this as a power series, I assure you, and I've just done it with Thomas to check it that it works. If you expand this as a power series, regarding this as f of z, you can calculate all the an, all the terms using Taylor's theorem, an, or it'll be f of n, nth derivative over n factorial. And you write it out, you'll see the coefficient of 1 over z works out to be exactly the same number, 1080. That's the meaning of the residue in the first place. All right, let's just pause and ask ourselves some questions now. What have you got to ask? You've got to be patient with listening to me droning on and on for several weeks now. What do you think about what we have done? If there are any questions to ask on it. I didn't promise you. I advertised at the very beginning that we were able to compute an integral without actually doing an integration. That's exactly what we've done. If you find the residue, you're not finding an integral. It gives you the answer for an integral, but you're not doing an integration. In fact, I'll show you some examples that are totally resistant to the integration methods you come across in first year. In first year, you did a whole string of integration methods. Integration by parts, partial fractions, dividing the denominator, substitution by the t. You can be quite clever in some cases. Sometimes you transforms the term, all kinds of tricks in integration. But here, you don't have to use any of the tricks. And indeed, of course, not all integrals can be computed. Like if you want to compute the integral of 1 over square root of, or leave 1 over. Let's just take the integral of square root of x to the power 7 plus 1 dx. How do you integrate that? Root x plus 7, x to the 7 plus 1. Root x to the 7 plus 1 dx. If you find a method to integrate that by hand, you will be a genius. Quite difficult to integrate that. I don't even know if it can be done. You might find some of these things become very complicated hypergeometric functions and stuff. So it's tricky. Integration is not trivial. Differentiation is trivial, of course. Now, let me show you how you can evaluate some real integrals. Okay. Let me do this first. I had another nice example. It's very powerful, but let me rather deal with some theoretical aspects first. Evaluating real integrals, real value integrals. Okay. These would be like rational functions. Some of these can be done with elementary techniques, some of them cannot. Where we can do it, I'll try to show you that it works in both ways. Now, we're not going to consider all possible types, but there are certain ones that fall into the theorem. So let's set it up like this. Say, consider the integral of the type minus infinity to plus infinity. Straight away, we're looking at a dangerous animal here, minus infinity to plus infinity. And suppose you have some function, numerator of x over denominator of x, dx. Where n and d are polynomial functions. Polynomials. And one, d has no non-real roots. In other words, d has no real roots. You guys will think, yeah, she's a crazy. I didn't just say it has no real roots, but I didn't say no non-real. It's to be precise. No, I mean to say it has no real roots. That's right, that's quite stupid, in fact. I want to say that there's no real roots. In other words, that is, what can you infer about a function? Suppose you have some function which has no real roots. What can you say about the roots? I mean, there's no. So if you take a thing like a long polynomial and factorize it into its parts, and none of the roots are real. So it's all like z plus I, z minus 3i, z plus 5i, and such. What can you say about such a thing? You can say something more than this. It's just a polynomial. It's a certain type of polynomial. What can you say about unreal roots or complex roots? How many of them are always present? Two. There's always two present. Conjugate pairs. Remember that here? Complex roots always occur in conjugate pairs. So you can't just have one of like z minus I. You will also have for 3 z plus I. Must be there somewhere. You can't just have z minus 3i, z plus 3i will be somewhere. You can't just have z minus 1 plus I. Z minus 1 minus I perhaps will be somewhere also. So they appear in conjugate pairs. So effectively, D is even because complex roots occur in conjugate pairs. So basically, at the bottom, you'll have a function like x to the 4th plus something, or x to the 6th plus something, x to the 10th plus x to the power 8 plus x to the power whatever. It'll be an even kind of polynomial. When you factorize it, there'll be pairs of brackets. There'll be an even number of brackets. There must be an even number of brackets because I said there's no real root, so that means all the other roots are complex, and complex roots must be in pairs. So you'll have an even setup. And the second requirement to hit this thing with a theorem is that the degree of d, the degree of the denominator, must be more than the degree of the numerator by 2. Must be. So you can have like x to the 6 at the bottom, but on the top you can only have up to x to the 4th. It must be more than 2. You can even have x to the 1, x cubed. I'll show you there's a funny problem if you have x cubed, like this here. You can have integral of x squared over x to the 6th plus 1 dx. That's okay. This is fine. Not this x to the 5, 2x to the 5 over x to the 6 plus 1 dx. That's not good. In any case, does anyone know the answer to the second one? What's the answer here? Anyone answer? You see the answer. Anyone knows what the answer is going to be? Integral of 2x to the 5 over x to the 6 plus 1. You can hit this with some substitution from first here. Let u equals to x to the 6 plus 1. du 6x to the 5. Cancel the x to the 5. Calculate the integral. But that will be quite long since you know some new stuff in third. Recall the story about odd and even. Integrate an odd function from minus a to plus a. What's the answer? 0. Integrate an odd function from minus a to plus a to 0. So this guy is actually odd. This guy is even. Odd over even. And if you change x into minus x, there'll be a minus sign appearing. So it's going to be an odd function. So integral of an odd is going to be 0. So then if you have x cubed here, a similar thing happens. If you have x to the power 1 here, same thing happens. Because it's odd. So we put even functions deliberately at the bottom to make our theorem work. This theorem can only work for this kind of case, where the degree of the denominator is at least 2 more than the numerator. And there are many of such cases appearing in applicable situations. Where was I? Yeah. So that's the setup. Consider that. So that's the build up. Now to integrate. In other words, to do the integral from minus infinity plus infinity of something n of x over d of x dx. What we do is we treat as complex poles and we surround each 0 in the upper half plane by a semicircle contour. That's the method. So you have a situation like this. You've got, say, poles where the denominator becomes 0. So you have one there. Of course, you'll have a mirror image here, right? If you've got a pole here, say 1 plus I, 1 minus I would be a corresponding pole here. There'll be an image of it. If you've got a pole here, say minus half plus I, there'll be a reflection here. Because complex poles, complex roots appear in conjugate pairs. So the trick is, you surround the upper half, surround the poles in the upper half plane by a semicircular contour like that, of some radius, say r, that goes from minus r to r. So here we have a contour along the circle, CR. And here we'll have the integral from minus r to plus r. Effectively, what I'll be doing is that I'll have an integral from minus r to plus r, and I'll try to make r go towards infinity. If r goes to infinity, then I've got to think at this minus infinity to plus infinity. Of course, you're wondering, what about the semicircle part? What will be the integral along the semicircle? Don't worry, all will end very well here. That integral works out to zero. The integral along the semicircle part will work out to be zero. So, but let me prove that next. Let me first establish this theorem here. So we can say by the residue theorem, let's just jot this down first. The integral from minus r to plus r, this is the straight line part now, of n of x dx over d of x dx, plus, now the complex part along CR will be n of z d of z dz. And this, according to the residue theorem, is 2 pi I sum of the residues of f of z z equals to zk, from k equals to 1 up to n. But, right, so I got the integral of this part here, and then I got the integral of this part here. I summed them up. Of course, this direction is this way here. So minus r to plus r, right? It's a closed contour now. Start up at this point, go along the circle, come here and come back. It's a closed contour. Now, you may be wondering, what about the lower half of the plane? Why is he focusing on the upper half only? Well, it turns out you can do the same thing for the lower half, except that the contour direction is different. It's the other way around. You can go like that, and this way here. Opposite direction to make a closed part. And you get the same answer. The minus part will negate any problem that we have in the top half, and you'll get the same answer effectively. So the name of the game is to surround the upper half of the poles with a circular contour. Circular contour because it turns out that the integral along the circular contour of n of z over d of z dz is 0. This one will be proved shortly. I'll prove this. Therefore, our theorem tells us that the integral from, this is 0 as r goes to infinity. So instead of having minus r to plus r, I can have minus infinity to plus infinity. N of x over d of x dx is also 2 pi I sum of the residue of f of z, z equals to zk, k equals to 1 to n. So far, you're not quite clear why I said that the degree of the denominator must be 2 more than the numerator. So now, I haven't given a justification for that. I will justify it in the proof. This proof only works if that happens. this integral here becomes 0 only if that is the case. Well, let me prove that. I think I wrote the proof up. Here's the proof. So this is the important part here. You may want to highlight this because you're going to be using this theorem a lot, even in chapter 3. Most of the functions that will appear there will be something like a rational function, something over something. Then you'll have to use this theorem. This lower half of the plane will come back in the picture in the next, in the sequel. I will use a thing called Jordan's complex conjugation to actually deal with that. So don't be too disheartened that I'm not speaking about it much now. I've said basically that the orientation will be in a different direction, but there's a trick to handle that. But it's not, it doesn't belong in this context. Now let me prove this statement. Obviously you will not be pleased if you can't prove it. I was thinking of not proving it. Then I said, well, this whole theorem rests upon the denominator being 2 more than the numerator. So it'll be a bit of a damn scoop if you don't prove it. So theorem. Integral of CR 0 of n over d is 0 if CR is a semicircle and if degree d is more than the degree of n by 2. Yeah, okay, that's enough. Proof. So if I expand n of z over d of z, recall they are polynomials. So there will be something like an z to the n plus an minus 1 z to the n minus 1 plus blah, 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 all the way up to a naught. Likewise, the bottom one will be some bn z to the n plus bn minus 1 z to the n minus 1 plus blah, 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 all the way up to some b naught. Expand them as a Taylor series if you like, but they are polynomials. They have finite start and end. Then I pull out, well, they don't have to have the same order, right? This one has to have order 2 more. So let's just call it m, rather. Let's put that as m. So on the top, I take out z to the n. At the bottom, I take out z to the m. What's left here will be, on the top, an plus an minus 1 z to the minus 1. All the way up to b z to the minus n. Not b, why did I say b? A. All the way up to there. Okay. Likewise, at the bottom, we will have bn plus bn minus 1 z to the minus 1 all the way up to b naught z to the minus n. I can just call this for short 1 over z to the m minus n. And this thing in brackets, let me just call him g of z. Note the limit of g of z as z goes to infinity, 0. Well, sorry, it's not 0, it's an. Oh, yes, these guys are 0. All these guys here are 0. 1 over z, 1 over infinity, all of them. So what survives? Just these two guys, an over bn. An over bn. It's not 0, it's an over bn. So for large z, there exists That symbol means there exists, the backwards E. There exists an upper bound, B, let's say B, such that G of Z is less than B. So there's some big number up there where this guy can't go beyond. There's a limit. The limit means there's some number somewhere where this thing cannot go past it. It is a limit, the upper bound. I'm going to leave this in the calculation. Now let's come to a semicircle. Now, on a semicircle, we have Z equals to, let's say, R e to the I theta. Remember, that's the formula for a equation of a circle, R e to the I theta. And if you take dz, it will be Ri e to the I theta d theta. Ri e to the I theta d theta. So now, let's take the following. Let's take the absolute value of the integral of n of z over d of z. A proof might be quite boring, but it's quite interesting to see how it finally ends up and how the result is achieved. So I'm going to actually show that this approach is zero. That's what I want to prove. So the integral of this part becomes zero. So that means the integral along the semicircle is zero. And I've got the tools for the semicircle. The semicircle goes from naught to pi. Maybe we should write this down here. Naught less than equal to theta less than equal to pi. If it were a full circle, it's naught to 2 pi. So this here, now let me just be careful how we write this. This will be the integral of n of z. I can write that as, you see, I've brought it down to this form here. Look here. I've brought things down to that stage there. So it's some g of z over z to the m minus n dz, right? And remember the theorem that I used once before? I said that this is, I can actually switch this around. I can actually put the absolute values inside, so I can get g of z like this over z to the m minus n. Well, this part doesn't really matter. This one here does, dz. And that's less than or equal to the integral from naught to pi. Now I'll change the game. This g of z here, I can say it's g of, what is z? Z is r e to the I theta. R e to the I theta. Z to the m minus n is also r e to the I theta to the power m minus n. The dz is the magnitude of I r e to the I theta d theta. So far, you with us, eh? We can put the absolutes here. Now this g we know is bounded, so it's less than, as I said here, it's bounded. It's less than some number b. The numerator so far. This stuff, whatever it is, the absolute value of g is bounded by b. B is some upper number where it can't go beyond. So we can say this is less than equal to the integral from naught to pi b. What's the magnitude of r e to the I theta? It's just r. What's the magnitude of I r e to the I theta? It's just r. D theta. So this works out to be, now we're integrating with respect to theta, guys. So it's like, this is like a constant, b over I'll keep it as BR of R to the M minus N. Then you'd have theta, and the limits are 0 to pi. So this becomes pi BR over R to the M minus N. That's where the game ends. Now, since M minus N is more than equal to 2, the last quantity approaches 0 as R goes to infinity. Why is that? See, there's a 1 on top, BR to the 1 here. If this one was 1 also, it cancel, right? But if it's 2, there'll still be an over R involved here. And if you have over R and R goes to infinity, that becomes 0. So if you have a 3 here, R over R cubed will be R squared. Even that will go to infinity, will go to 0 as R goes to infinity. That's why we need this guy to be more than 2, because there is a 1 on top here. So if M minus N is bigger than 2, there will still be something over R in the game. That part, if you're dividing by infinity, is going to be 0. That's why I need M minus N to be more than 2. Hence, integral along the semicircle of N of Z over D of Z, dz is 0 if degree of D is more than equal to degree of N plus 2. Right, now we prove it. So now we can actually apply the theorem to actual problem. So we know that the integral of N of X and D of X, dx, actually can be linked to the residual of Z. That's a nice other interplay. You have a real value function connected to the complex plane. So that's quite an uncanny connection that we have discovered right now. All right, shall we take a 5-minute break? Let me do some examples. Okay.